All right. Felipe, I think you can take it away. All right.
Cool. Okay. Hi, everyone. My name is Felipe. I'm part of the Apple Cider team. I work on the photometry model, which is I'm going to showcase today. I also work with Model Fusion, which is hopefully the theme of your hackathon on Friday. And well, thank you everybody for coming. For this session, especially for this first part, I wanted to make something more chill because all the other sessions were too much content, I believe. So I'll try to make something more interactive, make you make groups, and then just do something by yourselves. The second part will be about the transformer model that we implemented on Apple Cider. Okay, so let's talk a little bit about photometric transient classification. The goal of this first notebook is to basically take you from how the ZTF dataset that we have looks like, what are some nice features about it, why does it suck for some classes, and then implementing a simple baseline feature-based classifier on it. This would basically serve as a purpose to, well, tell the story of what do we need, why do we need a transformer to tackle this problem. Another good question is, why should we care about photometry classification at all, right? Usually, most of the information is contained in the spectra. We can see the peaks related to absorption and emission of a given transient, and that basically characterizes everything you want to know about it. However, as probably everybody told you this week, you're entering an era in which the sheer amount of data will be so much that we will be unable to get spectra for all the objects that we observe. Therefore, we need to use the other modality available, the other data products, basically images, metadata, and photometry, to try to get nice classification, filter out the uninteresting objects for your science case, and follow up or prioritize the objects that you actually care for. Cool. There is another point, though, because just optical classification maybe is not enough, because, well, you can for sure classify a light curve with 100 days of span, but classifying a light curve with like 5 days or maybe 2 days is the hard problem. And we will try to tackle that a little bit with the transformer later. Cool. So what is photometry in the end of the day, right? It's basically this raw set here. It's for a given observation, a stamp of time, the flux measured, the error on that flux, and the band that the telescope used to observe that object that day. The key challenges here, however, is that we're dealing with a time series or a set of those packets of time flux, error, and band that is not very nice sampled. It's very irregularly sampled. Sometimes the sky is just not nice, so you can't observe the transient that day. Sometimes the seeing is very bad, or the error mass on top of the telescope is just very bad, so you have those big error bars that basically tell you almost nothing, almost no information. And well, you need to make a decision fast, right? You need to trigger that spectrograph, yes or no. So those are some of the challenges here. That is why the usual time series models that you see that people use in health, for example, or finance, won't cut it for us. And basically, that is the reason why we need a model built for those time series, which are very regular, which people call in the literature event-based time series models. Our transformer that I'm going to show you today falls into that class. So at the end of the day, we implemented a transformer encoder inspired by BERT, which was a big shot in the ML community, weaponized with a learnable time embedding to make that early classification easier. That's our goal towards the end of the day after we go through the first notebook. Okay, so the first things that you need to do in order to run the notebook is to install those packets here. We will basically need all the standard stuff, so NumPy and Pandas. The only bad stuff that you need to install is Torch. Torch is always bad to install because it's very system dependent. You're going to have trouble with it. Just raise your hand and I will try to help you. Okay, cool. I believe that everybody have access to this notebook, right? It's on GitHub now. Okay, so while I do the talking, you can go and install everything that you need. Very good. So first of all, I'm going to explain the pre-processing that we do with those raw light curves, and then we're going to explore the dataset together a little bit. Okay, So we have some raw observations, right? Time, flux, the area of the flux, and the band. We need to turn that into a tensor because that is going to be what a deep learning model will ingest in the end of the day. But first, we need to get rid of the noise in the light curve as much as we can. So the first thing that we do is to merge noisy simulations into one. Sometimes we have some light curves in which you have a big gap of like 10 days between observations, but in a single night, you have like 4 observations in the same filter. Sometimes you have good observations, sometimes you have bad observations. And that is why we first just take an average in a rolling window just to get rid of those big uncertainty points. So it's basically an average, a weighted average, in which the weight is the inverse of the uncertainty, such that you basically bias your data towards the ones with smaller uncertainty. So you're basically cleaning your light curve. Then we need to build a nice vector with features that are going to be interesting towards separating different classes, right? So we need to somehow encode time. We need to somehow encode flux and its error and the band. And the way that we're going to do this is the following. We have 2 features for time. The first one, the big delta t, corresponds to the time difference between the very first observation and the current observation that you care about. So that basically gives you time since first detection. That is the big delta t. Then you have the small delta t, and that one is the cadence of your survey. That basically measures the difference in time between 2 consecutive observations. So for example, if you have a survey that is, slower to slew the telescope, then those delta t's are going to be bigger. Then your model knows that it shouldn't freak out if it doesn't see an observation in a given time. On the flux sector, basically magnitude, according to our experience, is the best thing that you could use to encode your flux and its error propagated like this, because that gives some stability of the model. In some transients, you see big explosions. So you have a very small flux and then a very big flux at the peak. So that logarithm basically controls that. And finally, the band needs to be encoded mathematically somehow because it's going to be injected by the model, right? So the band is basically if you're using the G filter, the R filter, or the I filter for ZTF. And the simplest way to encode that information is to basically transform that into a vector. So it's what we call a one-hot encoding. So if you're using ZTF green, for example, that vector is 1, 0, 0. If you're using the red, it's 0, 1, 0. And you've understood the rest. This is nice because if you want to, for example, reuse the model, but for a different survey, you just need to change this vector right here. So if you want to move to Rubin, you just need to create that one hot encoded vector, which is bigger corresponding to the number of filters you're going to use in your analysis. So that is nice. For this data set that I'm using today for this presentation, I also computed the color in G minus R and R minus I, but I'm not using them, at least not in this notebook. I'm leaving them as like a free feature for you if you want to use it when you extend the model. Cool. So finally, your input tensor, whatever the model is going to ingest at the end of the day, is this 7-dimensional vector here, which is basically the logarithm of the big delta t, the logarithm of the small delta t, log of flux, the error on that, your one-hot encoding on band, and the color information that we omit here, so you get 7 in total. Okay, so that's basically it. That is what you're going to find in the data set that you're going to play with. Cool. So, well, you are all very used to machine learning, so I know that you need to standardize your data, right? So we have pre-computed averages and standard deviations, so you can z-score your data. You can also find that in the data set that I sent you. Cool. So which classes of transients are we interested in classifying? For this very toy problem, I am basically going to walk you through classification in 5 big buckets. We have thermonuclear supernova, which is supernova type 1a. We have core collapse supernova, which is a big family of different transients. So you have supernova type 1b, 1c, 2, 2p, 2n, so on and so forth. And then other confusing stuff that is basically here just to poison your model. So you have cataclysmic variables, which in some very specific cases can make your model mistake a big rise for a rise of a supernova, for example. We have a stochastic transient here as one of the examples. So again, same confusion. Maybe, it's your unlucky day and the AGN just decided to give you a flare that can confuse your model. And also tidal disruption event, which is an explosive transient, but on a longer time scale. Cool. So those are the classes that we're going to work with. So those functions here are basically utilities to basically make your life easier when you deal with the data. I won't go through them because that is just boring. Cool. So let's take a peek and look at what our light curves look like for ZTF anyway. So I created this utility function here that basically will take some random light curves from this data set and print them according to their small class, their broad class, and all the bands available for that observation. So as you can see here, I'm basically choosing to print 4 rows of transients. So you can have a visual representation of the data. And we're using the random seed 13. And this is how your transients in this data set look like. So the very first column here is whatever falls in the bucket of supernova type 1a, so thermonuclear transients. The second column is whatever we're calling here a quark flap supernova, and then the other confusing classes, right? So this is how they look like. If you want, you can just come here and change your random state to go to like this and print another row of transients. I will let you play around with this.
Can't actually do that because we don't have access to the data.
Really? On the drive?
It's not in the GitHub.
Yeah, it's on the drive that I sent on the Slack channel for day 3. Yeah. Okay, so our very first exercise, so we won't get too bored, is the following. We're going to train your magic brain as our first neural network for today, right? So we're going to basically make groups and discuss and learn how those transients look like in different scenarios, right? So you should be able to know your data set very well to the point in which you can actually look at those light curves and classify them by yourself. If you can do that by yourself, we shouldn't expect you to be able to code a network to do that, right? So let's get that skill ready. So this is going to be our first exercise. This is the cell where magic happens to generate the mystery light curve. So don't peek inside this cell, right? And well, your objective here is to basically train your eye to recognize transients based on rise, fall rates, peak, and bands available. The first part is going to be to train your neural net, your brain. So we're going to basically make you plot a lot of those light curves and just take a look at them and note different features. So the shape, rise, decay, and how the filters interact among themselves. And you're going to do that with your closest peers. So I would like you to make groups if you can. No pressure, like if you could collapse and just talk to your peers, the people next to you, that would be super nice. Yes. So I will give you some minutes while you do that. And the point here is we have, after you take a look at a bunch of them, we have a set of mystery light curves, right? I'm just choosing 7 of them for now. If you're feeling comfy, you can just, increase the number if you want to classify more. But your goal is to assign a class to each mystery curve, but not just like guess it. Try to justify your choice and ask for peer review for the people around you to see if their classification matches yours. So here we have those 7 curves. It should be the same for everybody. And yeah, so they all have very different features, right? So I can see that 2 of them are very clearly peaked. Others have a more constant flux. So basically try to guess which ones are which, basically based on those light curves here. So you have access to this notebook, right? It's on GitHub. Okay. If you have any problems getting it, just let me know. I'll be okay. So maybe we can talk a little bit about what's going on in those light curves. So first of all, I would like to know AJ's favorite number. What is your favorite number, AJ? 4. Okay, so that is going to be our random state. Skylar, how many rows would you like to see in this wonderful plot? What is your favorite number?
7.
7. Okay, let's do 7. And bada bing, bada boom, PD is not defined. So you run this cell. And hopefully, there you go. There we go. Okay, nice. So here we have a collection of many light curves belonging to many classes. So we can just take a look and discuss their behavior a little bit, right? So maybe can somebody tell me a distinctive feature of supernova type 1a that we can notice from those graphs? So if I take a zoom out here, we can see all the 7 light curves, hopefully. And although they are sampled to the same cutoff in time, they're all 100 days long. Some of them have very few data points, right? So this one here, for example, didn't receive a lot of love, right? Got only like 8 points or something. This one was very well sampled. So can somebody help me with a distinctive characteristic of light curves of supernova type 1a? Christina?
The upper left, the bottom left are actually really good. Like for team like hers for type 1A.
Yes. Would you say that they're symmetric or asymmetric? They look a little bit asymmetric, right? For some of them, yes. So another thing that we can notice is that it has a very distinctive rise rate and a very distinctive fall rate, right? Would you say that it falls faster or slower with respect to the rise? Slower. So that is a common characteristic. Another common thing is that usually we shouldn't see this big of a difference between the red curve and the green curve. That is usually due to an extinction in the host galaxy. So for example, this one here has a hint of a peak, right? And here you can see that they basically stay the same. Cool. That is probably a reason why this was very fastly classified. So they didn't bother taking more data points. This one, right? But okay, we can let hell get loose a little bit because now we're dealing with core collapse supernova and it's a big broad class, right? We put supernova type 2, 1b, 1c in the middle of them. Let's try to find at least a common factor that maybe our model would be able to identify. Can somebody give me a hint of maybe something in common between all of those light curves? Yes?
I mean, maybe the rise, there's like a constant rise rate, but the like decay rate is like it's kind of like flattened.
Exactly. Yes. So that is especially a nice characteristic of supernova type 2, especially the subtypes 2p or 2n. They get super, super flat. That is usually due to the presence of circumstellar material that keeps the supernova heated, so it keeps emitting light to us. So hopefully our model should be able to somehow figure, especially the deep learning model, to figure how to calculate a derivative for a fall rate to represent that this part of the light curve is very flat. So this would be maybe a nice characteristic. Another systematic here is that the fall rate for the red part of the curve is always very different from the green part of the curve. So that's nice. Okay, what about cataclysmic variables?
They sometimes have much sharper features.
Yes. So, for example, this light curve here is very, very flat until at some given instant in time, it has like this very sharp peak and then super sharp fall. So maybe that would be a candidate CV in our data set. They also don't receive a lot of love. So those here, they don't have many data points collected. And well, there might be a reason for that. Can somebody guess the reason?
Maybe it's because the time to like detect cataclysmic variables is only very short.
Yes, that could be. Another reason would be that nobody cares about those cataclysmic variables. We don't like them. Another reason could be that, well, the light curve, the constant light curve could be way below the detection threshold, right? And then only when it rises super fast, you can detect it. So a bunch of different reasons. Okay, what's going on with AGNs then? Super, super flat, right? And they have this kind of drifty behavior, you know, it gets a trend here and then goes slowly down. And this is what we call a stochastic transient. So it's literally doing a random walk. It's a drunk person walking in the sky like that. So it's basically what you can see in those light curves. So whenever you see a light curve very, very flat like this, we can pretty much guess it's an AGN. Does anybody know any other cool characteristics about AGNs? Maybe if you see a picture of the host galaxy, can you detect an AGN easily just by the picture? So what is an AGN at the end of the day? What's going on? Yes, and what is powering the active part? A black hole, and black holes live at the core of the galaxy. So we basically say that this is a nuclear transient, right? So if you have your light curve, you can be very unsure because it's super, super constant. But if you see the cutouts, you can see that those basically come from the nuclear part of the galaxy. So that is a nice way to distinguish AGNs from everything else.
Could you reiterate that again?
So let's imagine that I have a cutout here, right? So let's imagine that we have our science image, the ref, and the difference. And let's imagine that we have a very beautiful galaxy. Like this. Usually an AGN would come from the core of the galaxy. So we would say that it's a nuclear transient because it comes from the core of the place. So your reference image would probably look like that galaxy, but without the transient. And the difference would be just the shiny point in the middle.
And then how does that translate to I haven't seen AGN like first before, so.
Yes.
How does that
So-
translate to these?
That's a very good question because actually maybe photometry just sucks for classifying AGN in general, but images are very, very good. And that is one of the motivations for having a multimodal classifier like apple cider. Boom, opportunity attack. So if you mix your modalities, you can cover the weak spots of each modality. So AGNs are very distinctive by their images. If you combine those with photometry, maybe you can rule out those light curves altogether. Simple. I have an issue.
Well, that's first for everything.
Yes.
Are there group analyses such that like APN, the APN we can see are one that we can resolve?
Yes, there is also that question, yeah. And AGNs, at least in images, can be sometimes confused with tidal disruption events. So one characteristic that they have is that compared to supernova, they have a peak, but the time scale here of the rise and the fade is super, super dilated. So they have those fat peaks like this. They are very distinctive like this in photometry, but on the other hand, they just look like an AGN because it's also due to a black hole, so they also come usually from the center of galaxies. So yeah, this is basically how photometry plays around with the other modalities. Okay, cool. Now that we agreed of some nice characteristics of those transients, let's try to guess the mystery classes. I have here all those beautiful light curves. Okay, so let's analyze one by one. Okay, any good guesses for the first mystery transient? On what we talked? That would be a very nice guess. Why?
For that, right?
Yes, super, super flat, very lacking of any nice features. Cool. What about the second mystery transient? Cataclysmic variable. Oh yeah, you got it. Nice. What about the third one?
Tidal disruption, because it has like a flatter beat. Oh, yeah.
Okay, so we have some divergences here. I would like to understand your arguments. Very good argument. Yes. Okay, so one nice thing about this one is the scale. Remember, we should always take a look at the axes as well. So this light curve spans from 0 to 50 days until the last observation.
Oh.
Right? So
I'll change my answer.
yes, I will leave that one open for now. What about the fourth one?
AG1.
Very good, very good. And the fifth one, 0 to 20 something days. What did you say? Okay, that's a nice candidate. Why would you say that?
Little bit of peak, but in 0 to 20, it should, like, if you scale it to 100, it should be 5.
Very good. And the sixth one, any guesses? Does this one have a peak or no? It does, right? Yes, very clearly. Okay, it spans from 0 to 30 days. Can we see a lot of differentiation between the red filter and the green filter?
Only that last data point.
Only the very last data point, and sometimes it's everything you have. So let's keep this one in mind. And I would say the same thing about the last one, right? So, okay, time to review. The mystery classes were actually the first one an AGN. So you got it right, Christina, congrats. Then the second one was cataclysmic, congrats, Char, very good. The third one was a supernova type 1, actually.
I think I just didn't read that.
Yes, but this one was like kind of elusive because the red part has this weird bump here.
I have observed type one before, and it's like, if there's extra material, sometimes there will be a weird bump, and we don't
Yes.
always know why there's extra material.
Yes, exactly, and could be one of the weird supernova type 1 subtypes.
Yeah.
Yes, we do have all the flavors. Yes, what would you say?
I don't know, I think that's it, kind of looks like this.
Yes, very good. So fourth one AGN, everybody got this right. The fifth one would be a core collapse supernova, and yeah, thanks God we saw this last point because this one was very useful. The sixth one was 1A, and the very last one was also 1A. Cool. So, well, we just basically discussed why was that, or at least why in my weird mind I tried to justify the classes after seeing the labels. So basically that's it. Cool. So now that we know a little bit what features are able to basically split this class space, the next exercise for you folks is to implement a feature-based classifier. So your goal in this exercise will basically take the dataset and code with it and basically calculate features in the entire dataset. I have some suggestions for nice features here, such as basically statistics on the flux, or maybe some more domain specific, like a rise rate or a fall rate or whatever, and feed that to basically a classic machine learning solution. So a random forest classifier, a logistic regression, a gradient boost, whatever you prefer, and basically make a classification report out of that. So plot me a loss curve, plot me, I want to see basically accuracy, recall, precision, all of those fun stuff. So this is basically what we're going to do until the break. I know that you're probably doing your own stuff there at your laptops, but if you have any questions about trying to implement this, I will be here. So good luck with that.